This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
This is a podcast of Scripps Institution of Oceanography at UC San Diego. To learn more about how you can support Scripps, visit us online at scripps.ucsd.edu.
What we're doing is we're measuring ambient aerosol from the atmosphere. We have an inlet, so we're pulling particles in from the outside atmosphere and down into this instrument. And we actually are doing two types of measurements at once to compare.
At the end of the Scripps Pier, one crowded with mini labs, radar towers, and meteorological equipment, atmospheric chemistry professor Lynn Russell and her students have been busy analyzing air. Specifically, they are interested in the tiny airborne particles, or aerosols, that winds are delivering to the pier.
We're measuring the total particles all below 1 micron, and these particles can come from many different sources, both from sea salt and sea spray, from the continent, both from dust and also anthropogenic activities, man-made, like soot, fossil fuel burning, cars, all those types of activities on land contribute to the total particles we're measuring here right off the coast. So we're also getting emissions from ships that travel up and down the coast, and transport from Los Angeles of their particles that they emit from their cars and industry and whatnot.
This is the Scripps Pier here, and by using calculations of where those aerosol particles came from using wind trajectories, this is Los Angeles and this is Las Vegas, and we've identified that a large fraction of those particles have been coming from this I-15 corridor. The bright red colors indicate the highest concentrations of organic particles. And in particular, this is the signature of carboxylic acids, a specific type of organic particle that we've been focusing on.
The pier is just one place in which Russell is analyzing aerosols, which can absorb heat or reflect light and serve as the skeletons on which clouds assemble. Often moving along paths of atmospheric water vapor, aerosols influence atmospheric warming and cooling, rainfall and snowfall, sometimes thousands of miles away from their points of origin. But the chemistry and physics going on in this process is so poorly understood that climate scientists consider aerosols' effects on clouds to be the top source of uncertainty in climate simulations. Russell is especially interested in organic aerosols, which can be made by anything from plants to diesel-burning engines, all with various effects on atmospheric chemistry. Recently, she has traveled to urban and rural areas in North America to characterize which natural and human-made aerosols are in the skies at any given time.
Aerosol particles have the direct effect of reflecting light themselves, but they're also an important part of clouds, and clouds are a key part of the climate system that serve both to reflect sunlight and to insulate the Earth, as well as to cause rainfall in different regions. And in those many roles, the composition of the particles as well as their size is key, and the number, how many are there. And so the particles that can form cloud droplets we call cloud condensation nuclei. And by putting more of them in the atmosphere, you end up making clouds with smaller droplets because you have the same amount of water and you're now spreading it out over a larger number of particles. It's clear that some of the changes in regional rainfall patterns are correlated with changes in particle emissions in urban areas.
Russell also takes samples of air that carries pollution from Europe and Asia to the Arctic Circle and creates a condition known as Arctic haze during spring. From a field station in Barrow, Alaska, and a research cruise in the Norwegian Sea, she has made important discoveries in this past year. Nutrients and products of ocean phytoplankton are the dominant source of organic aerosols over the Atlantic much of the year, but Russell also witnessed on both oceans how the human influence extends even to the planet's most remote reaches.
One of the most interesting things is in spring you see a lot of particles from the Asian continent, And those Asian particles often show both dust and biomass burning, probably from the Siberian region typically, as well as some industrial influences. Over the summer, the concentrations drop way down so that you get very few particles in the summer. In the winter, they pick back up again with wind speed, and so those particles are probably more of natural origin. And being able to track that over the entire course of 4 seasons in 1 year has given us a lot of really new and interesting information, and it has helped us to better understand the reflection of sunlight by particles over as part of the Arctic haze in the Barrow region.
Last fall, Russell joined colleagues to form the Aerosol Chemistry and Climate Institute, led jointly by Scripps and the Pacific Northwest National Laboratory. The number of researchers joining the quest to understand aerosols is growing to match the complexity and scope of a topic vital to our understanding of what climate will do next.
Really being able to bring those together and to understand the big picture is the only way that we're going to be able to reduce the uncertainty associated with aerosol particles and their effects on climate. Just because there's so many parameters, there's no one instrument or even one person who can do all of it at once. And so it's important to have a good collaboration as part of this.
This has been a presentation of Scripps Institution of Oceanography at UC San Diego.